As promised during my office hours last week, today I'm just going to really quickly walk through the solutions for midterm 2 from 2016. So I'll just start by putting down my name, which is Brent E, and then writing my SID, which is 26858652. Okay, so let's look at question 1. So question 1, part A, asks us to write the matrix form of this transformation e to the omega hat theta for omega is equal to 001 transpose. It also wants us to describe in words the motion it represents. So just looking at this transformation, this matrix exponential, we'll note that this is in the same form as what our Rodriguez's formula tries to solve. So we know that this is a rotation about the omega axis by theta. And because omega here is just 001, or the z-axis, we just get a rotation about the z, rz of theta, which we know to be cosine theta, negative sine theta, 0, sine theta, cosine theta, 0, 0, 0, 1. And you can either have memorized this or find it on your cheat sheet. Next, we want to describe in words the motion it represents, and we can just say that this is a rotation about the z-axis by theta. And that's it for part A. Next, I'm going to skip part B and C just because we didn't really cover the material the same way, specifically what we do with these non-normalized omegas. So you won't see a similar question on our actual exam this Thursday, but I'd encourage you to try these problems out anyways. Okay, so let's look at part D. And part D asks us to find the matrix form of this transformation, e to the twist hat theta, for twist is equal to 0, 0, 0, 0, 0, 1 transpose. And we'll know that these first three are the translation terms, which is v, and that's all zeros, so all this gives us is a rotation about the z-axis. So the solution for this should look pretty similar to our solution for part A. So first, we'll just write out the general form of this, e to the twist hat theta is equal to this homogeneous transform with 0, 0, 0, 1 at the bottom, right? And then the translation term, again, here is all zeros, so we can fill this right column with zeros. And then all we have to put here is RZ for the rotation. So we know that RZ from earlier is cosine theta, negative sine theta, 0, sine theta, cosine theta, 0, and then 0, 0, 1. And that's it. Next, we have part E, which again asks us to find the matrix form of this transformation, e to the twist hat theta, given a twist vector which now has screw motion. So this has both the v and the omega. And they both only have terms in the x-axis. So from class, we know that there's a closed form solution for this matrix exponential, which is on your cheat sheet. So that's e to the omega hat theta, I3 minus e to the omega hat theta times omega cross v plus omega transpose v theta. And then at the bottom, we have a 0 vector transpose and then a 1. So looking at this a little bit more closely, we note that omega transpose v here is the dot product between omega and v, which just gets us 1, right? Because we're taking 1, 0, 0 and taking the dot product of that with 1, 0, 0. We also notice that omega cross v here just becomes a 0 vector because omega and v are equal. And when you take the cross product of two equal vectors, you just get 0. So this entire term disappears because it gets zeroed out. And the second term just becomes omega theta. So let's rewrite this. E to the omega hat theta, and then omega theta, 0 vector transpose, and then a 1, right? So e to the omega hat theta, we can solve with Rodriguez's formula, or just by noticing that this is on the x-axis, so we can write this as rx of theta. Omega theta, because omega is 1, 0, 0, we can write as theta 0, 0. And then again, we fill this bottom with zeros and put a 1 at the bottom, right? And then if we just fill in our solution for what Rx is, we get that this guy should be 1, 0, 0, 0 cosine theta, negative sine theta, 0, sine theta, cosine theta. Then all zeros at the bottom, a 1 at the right, and then theta is 0, 0 for the translation. And that's the answer for part E. I think that's all for number 1. Let's look at number 2. This time it's a question on forward kinematics, and we want to refer to some manipulator in the appendix. So part A asks us to use matrix exponents to write an expression for the forward kinematics map GWT of theta. So we can write GWT of theta, and we know that we can always find GWT of theta as some mapping from GWT of 0. So we know the initial configuration, and we want to parameterize it by the joint angles in theta. And so looking at the appendix, which has a manipulator in it, we see that it has 3 revolute joints, which are twist 3 on the outside, and then twist 2, and then twist 1. Okay. So we can just use our standard exponential mappings here. So we have e to the twist hat 3, theta 3, e to the twist hat 2, theta 2, e to the twist hat 1, theta 1. Note that the order does matter here. We always want the outermost joint on the right side of that mapping. Okay. And then part B asks us to find GWT of 0, which is the initial configuration. So we can look at the manipulator and try to figure out what this initial configuration is. So we know that GWT of 0, it should have the form of R and then P, 0, 1. Right, so R here is the relative rotation, and P here is the relative translation. And looking at the coordinate frames, so this is the roll frame and the tool frame, we see that there's no rotation between these two because all the axes are pointing in the same direction. So this R here should just be the identity. Then for P, we have this translation in the x-axis, and then this upwards movement in the z-axis. And there's no translation in the y-axis. So what we should get is some value in the x, then 0 for the y, and then some value in the z. And if we scroll down here a little bit, we can see that this z offset is L0, and this x offset is L1 plus L2. So we get L1 plus L2, and then L0 for z. And then just putting all this together, we can write GWT of 0 is equal to a rotation, which is the identity matrix, and then a translation, which is L1 plus L2, 0, and then L0. And then to make it homogeneous form, we put all zeros and then 1 at the bottom row. So let's look at part C. So part C wants us to find each of the twists for the 3 joints. Let's just do this directly on the diagram. So we want to find the values of twist 1, twist 2, and twist 3. And we know that the form of a twist is some linear component at the top and then an angular component at the bottom. This linear component for revolute joints we can also often find with negative omega cross Q. Okay, so let's just write out the megas for each of the joints. We'll start with joint 3. We notice that it's pointing in the positive y direction, so we have omega is equal to 0, 1, 0. Same for joint 2, omega is equal to 0, 1, 0. And then for twist 1, we have it in the positive z direction, so omega is equal to 0, 0, 1. Cool. So V for joint 1 is easy because if we do negative omega cross Q with Q at the spatial origin, we get just 0, right? Because the point Q is all zeros, so the cross product of anything with it is also all zeros. Now let's look at something a little more complicated. So we can do twist 2. There are multiple ways to do this. We could do this with a negative omega cross Q, but we could also compute this twist with a circle trick. So we can center a circle at the joint, and then pass it through the spatial origin, like that. That's a target circle. Like that. Okay, like that. There we go. Okay. And then if we use the right-hand rule to compute which way it's rotating, so this is the positive direction, right? Then we'll draw a tangential vector at that spatial origin. And this vector right here represents the linear component of our twist. So we have this length is equal to the radius, which is L0. And so V for twist 2 is in the negative x direction. We get negative L0, 0, 0. You can do the same thing for twist 3. Again, use the circle rule. So we center at the joint and pass the circle through the spatial origin as such. Again, a positive rotation is in this direction. So we have a tangential vector from the spatial origin, like so. Now we want to break down the components of this. So it has both a z component, right, and also an x component. And just by looking at this similar triangle right here, we get that this x component is L0, and this z component is L1. And so V for twist 3 should be equal to negative L0, 0, L1. And again, you can compute this exact same thing with negative omega cross Q. So just putting them all together to write our solution, we should get that twist 1 is equal to 0, 0, 0, 0, 0, 1, right? There's no translation here. Twist 2 is equal to negative L0, 0, 0, 0, 1, 0. And then finally, twist 3, you should get that negative L0, 0, L1, 0, 1, 0. And that's the solution for part C, and all there is to the forward kinematics section. Okay, now let's look at question 3, which is on inverse kinematics. So the first part of it wants us to find G1 as a function of our desired configuration GD, WT, and any other known configurations. So this should be pretty straightforward. We know that GD, WT is equal to the exponential mapping of each of the joints times the initial configuration, right? You'll notice that these three terms is just G1, so G1 is just the exponential mapping. And to isolate G1, we can just invert GWT of 0 and right multiply it to both sides. So that gets us G1 is equal to GDWT multiplied by GWT inverse of 0. Part B of the question wants us to write down the invariant points of the system and the joints they're invariant to. So let's look at the diagram and recall that a point is invariant to a joint if a transformation induced by that joint can never affect the actual coordinates of the point. So for a revolute joint, a point is invariant to the joint, basically if it's along the axis of rotation, right? So if we have a point here and we rotate it about the joint, that point's not going to move. So for this specific question, we can basically say any point along an axis of rotation is invariant to that axis, and then this intersection right here is invariant to both twist 2 and twist 1. So let's go back, and we'll say that any point along an axis of rotation is invariant to the corresponding point or corresponding joint. I'm terrible at spelling. Corresponding joint. And then we also have this specific point right here, which is invariant to two joints. So we can call this like P shoulder. And its location is equal to 0, 0, L naught. 0, 0, L naught is invariant to joints 1 and 2. So now that we have the invariant points, we can maybe use that for finding the PK subproblems. So part C asks us to find theta 3 using a PK subproblem. And we want to find all the necessary terms to compute theta 3. Okay, so let's look at the manipulator again. Theta 3 corresponds to joint 3 right here. And one thing we can notice is that joint 3 is the only thing that controls the distance between the end effector and that invariant point P shoulder that we just defined, right? If we rotate along joint 1, all that does is rotate in this circle. That doesn't change the distance. If we rotate along joint 2, that just rotates in this circle, and again, doesn't change the distance. So because joint 3 is the only thing that controls that distance, we can use the PK3 subproblem. And what we need for PK3 are a couple of terms to set it up. We need a P, which is a point that we're moving. Q, which is that center of the sphere or that point that we want a certain distance away from P. We want R, which is just a point along the axis of rotation. We want delta, which is the desired distance. Then we want some twist, right? So let's just go on the easy ones first. So the twist is just twist 3, right? Because it's rotating along twist 3. R is just a point along twist 3, along this axis of rotation. So we can set that to just the coordinate of a point here, which would be L1 in the x-axis, anything for the y-axis, and then L0 for the z. Delta here, we want the desired distance between the end effector and the shoulder. And we can compute that by just taking the desired end effector position, G1 P end, subtracting the ultimate shoulder position, which never changes, so P shoulder, and just taking that distance. Right. So each of these terms are known. We know G1, which is a mapping from the initial configuration to the desired configuration. We know P end, which is just the end effector position in the initial configuration. And we know P shoulder, which is just a constant position of this shoulder. Okay. So for P and Q, logically from that, we want P end for P and P shoulder from Q. So what we're basically doing here is we're defining the sphere around P shoulder, right? With a radius of delta. We're trying to move this end effector point to something along the sphere. And the idea is because twist 3 is the only thing that controls the distance between P end and P shoulder, if that distance is correct, which we can ensure with PK3, then that value of theta 3 is also correct. So let's just define these terms numerically, and then that'll be our answer. So P end will be L1 plus L2 for the x, right? 0 for the y, and L0. I just did that by inspection, so this is the x, this is the z, and then there's no y coordinate. P shoulder, we know from earlier, that's 0x, 0y, and then L0 for the z. And that should be it. We can just take this answer, and then copy it over to our solutions. So that's it for theta 3. Now we know theta 3. And we want to somehow use that to compute theta 1 and theta 2 for part D. So let's again look at the diagram. Clean up a little bit. And we see in this diagram, one thing that's pretty clear is that axis 1 and axis 2 intersect each other at a point. And we also want to solve for them simultaneously, which is kind of implied in part D. And you should be able to pattern match this with PK2. PK2 requires that we're trying to move a point from one location to another using two joints that intersect. So let's try to set this up as a PK2 subproblem. For PK2, we again need a P, we need a Q, we need a twist, and then we need an R, right? So Q should be straightforward. We just want to move this end effector to the final desired position. So that's just G1, P end, right? Where P end is in the initial configuration, and G1 maps that to the desired configuration. The twists are twist 1 and twist 2. And then R is the shoulder point. So for PK2, R is just the intersection point. And that we use 0, 0, L0. Transfers. Finally, for P, this guy should be basically the end effector position, but with theta 3 applied, because we know theta 3. So this should be e to the power of twist 3 hat theta 3, so both of these are known, multiplied by p end. So what we did was we used twist 3 to move the end effector position to the correct distance away from the shoulder, right? That way we know that theta 3 is correct. So it's somewhere along the sphere that has the desired end effector position on it. And then we use twist 1 and twist 2 to rotate it along the surface of the sphere. And after these two steps are done, we should be left with a correct inverse kinematic solution. Oops. Okay, that's a bit of a mess. I wonder what happened here. Okay, there we go. Yeah, so I think I just got tripped up a little bit there because I think the solutions for this P is actually incorrect. It should be P end with theta 3 applied, not just P end. I'll put a correction on Piazza or something if I made a mistake here. Yeah, let's move on to the next question, which is question 4. And this question looks at the Jacobians of the manipulator shown in Appendix 1. So again, this is the same manipulator as before. And the first part of it tells us to write the spatial Jacobian for the manipulator in its initial configuration. Figures 2 and 3. Let's look at figures 2 and 3. And that's just these guys. And we know that the spatial Jacobian, JS, is just equal to the twists stacked vertically next to each other. Right? And we can put primes here to say it's in the current configuration. But because the current configuration is the initial configuration, this should be the same thing as twist 1, twist 2, and twist 3. We already solved for these earlier, so we can just take our solution from above and stack them next to each other. So what the twists were, we just take these 3 twists and put them next to each other. So this should be 0, 0, 0, 0, 0, 0, 0, 0, 1, negative L0, 0, 0, 0, 1, 0, negative L0, 0, L1, 0, 1, 0. So all we did was we looked at the twists we've already solved for, and then we copied them over. Okay. So the next part wants us to write the body Jacobian for the manipulator in this configuration. This is going to require a little bit more work. We have a couple options here. We could, one, take the adjoint and try to translate from the spatial Jacobian to the body Jacobian. But the easier way is probably just to look back at the manipulator and compute the Jacobians from scratch. We can do this with the circle method. I'm not going to go too far into detail of how this works. I'll try to get a Piazza post up that has a more detailed walkthrough of the circle method. But basically, for each joint, we're going to draw a circle that's centered at the joint and passes through the end effector. So for twist 3, right, we're going to center a circle here, pass it through the end effector, and use the right-hand rule to figure out the tangential vector that describes the linear component. Okay, so for twist 3, we have a rotational component, which is this axis, which we know is 0, 1, 0, expressed in the tool frame. And then we have this tangential vector as linear component, also expressed in the tool frame. And we see that this is the negative z direction, so this should be negative L2, 0, 0. And basically we know the length of that vector because it's equal to the radius of the circle. So this circle is L2, and so this guy is also L2. Okay, so let's do twists 2 and 1. So twist 2 is pretty much the same thing, right? We have a joint here, and we draw a circle, or I drew only part of the circle, but you should get the idea. And then we have a tangential vector. Only this time, instead of length L2, it's L1 plus L2. we just write the same thing, but we change L2 to L1 plus L2. And that gets us L1, negative L1 minus L2 for the Z component, and then 0, 1, 0 for the rotation. Again, this is all expressed in the body frame. It just happens in this particular case that the body frame and the world frame have the exact same orientation. Okay, and then finally we have to do it for L0. So this is going to be a little bit weirder, but we'll try to draw a circle in 3D. So we draw a circle centered at this joint, right? Then it passes through the end effector, right? And then we have a tangential vector like this. And that's in the positive y direction. So we get that twist 1 is equal to 0, and then L1 plus L2 in the positive y direction, because this length is equal to this length, right? This is L1 plus L2. So this is also L1 plus L2. 0, L1 plus L2. We have no z component. And then the axis of rotation is 0, 0, 1. So to write the body Jacobian, all we do is we write JB is equal to these twists stacked together. Twist 1, twist 2, twist 3. Right. And these should all have daggers to indicate that they're in the body frame. Yeah, so we'll just stack them together and that'll be our answer. So twist 1 dagger is 0, L1 plus L2, 0, 0, 0, 1. Twist 2 dagger is 0, 0, negative L1 minus L2, 0, 1, 0, 0, 0, negative L2, 0, 1, 0. And that's our answer. So let's just copy this over to here. There. So that's our body Jacobian. And so that's the answer to part B. And now we want to answer if this is a singular configuration or not. And if it is, we want to give an expression for the linear dependency between the columns. Okay, so let's just look at it by visual inspection. The rank of the spatial body Jacobians should be the same, so it doesn't matter which Jacobian we look at. I'll just look at the spatial Jacobian. And we see that the rank of it is 3 because they're not linearly dependent. So this first twist can control the omega z, right? The second twist can control the omega y, and this final twist can control L1, or sorry, vz. So given that, we can say not singular. And we want to show that the columns are linearly independent. And to do that, we can just say for the spatial Jacobian, column 1 uniquely determines omega z, right? It's omega z. Column 2 uniquely determines omega y, right? It's omega y. And then column 3 can uniquely determine let's say vz. And that should be enough for the answer. The answer and the official solutions are probably a little bit different from this, but there's a lot of ways you can write this, so it's pretty open-ended. Cool. So that's parts A through C. Part D asks us what the relationship is between twist, twist prime, and twist dagger. It also asks us what each of these matrices represent. Okay, so let's just define them. These are really, really important, so you should know all of these definitions. So the twist is just a normal twist, right? When we use this for inverse kinematics. All that is a spatial twist in the initial configuration. So this is when all the joint angles are 0. Twist prime is what we use for the spatial Jacobian, and that is just the same thing. It's a spatial twist in the current configuration, right? So when we have all the joint angles equal to 0, twist prime and just regular twist are the same. Twist dagger is equal to the body twist, again in the current configuration. I think the official solutions for this midterm are wrong here, in that they say it's in the initial configuration. But yeah, so once we know these, defining what M1, M2, and M3 are is pretty straightforward. So M1 and M2 are both spatial Jacobians, right? But M1 is in initial configuration, whereas M2 is in the current configuration. M3 is also in the current configuration, but it's a body Jacobian. So each of these velocities in the Jacobian are represented with respect to the body frame. And that's it for question 4. So that is inverse kinematics. Next, let's look at question 5, which is on velocities. So part A asks us what instantaneous linear body velocities are possible in this configuration. Because these are body velocities, we can look at the body Jacobian. And we see that if we took a linear combination of these 3 columns, we could set Vx, Vy, and Vz equal to any value. So this first twist can control Vy, the second twist can control Vx, and the third one can control Vz. So we can just write Vx, Vy, Vz, or all of them. 5b asks if this robot is in a singular configuration. And the answer there is no, because we can independently control Vx, Vy, and Vz, and that gives us a Jacobian rank of 3. So we can write no. We look at this a little more in depth. So theta 1 dot controls Vy, as we saw earlier, right? Theta 1 dot controls Vy because it corresponds to twist 1. Theta 2 dot controls Vx and Vz. And then theta 3 dot controls just Vz. And if we look at these, we can see that we can control Vx, Vy, and Vz all independently, just using a linear combination via theta 1 dot, theta 2 dot, and theta 3 dot. Okay. Part C asks us to show that this matrix M relates the velocity of a point with the coordinates of that point, both seen in the body or tool frame. So recall that if we have a body velocity of a point, let's say VBQT, we can map that from the coordinates of that point using this big V wedge in the body frame WT. So this is saying big V wedge here is this body velocity of the tool frame as it's moving with respect to the world frame. Okay, so now we just have to show that M and this big V wedge are equivalent. And we can do that by first computing big V BWT as the body Jacobian multiplied by theta dot, right? And to do that, we are just taking a linear combination of these 3 columns, each scaled by their respective joint velocities. So this first twist is scaled by theta 1 dot, the second twist is scaled by theta 2 dot, and this third twist is scaled by theta 3 dot. And if we compute that, we should get negative L1 theta 2 dot, L1 theta 1 dot, negative L2 theta 2 dot plus theta 3 dot, 0 theta 2 dot plus theta 3 dot, and then theta 1 dot. Okay. And then if we wedge this, VBWT, we get a 4x4 matrix where these top 3 is, or this first 3x3 here is equal to omega skew, where this is omega, This here is P, where this is P, and the bottom is all zeros. Okay, so let's just do that really quickly. First, we'll just fill in the zeros because that's easy. Then we'll skew omega. We put zeros down the diagonal for that. Have negative theta 1 here, theta 1 dot here, negative theta 2 dot here, minus theta 3 dot, theta 2 plus theta 3, each dotted, and then 0, 0. And then for P, we'll just take these three, slap them in here, negative L1 theta 2 dot, L1 theta 1 dot, negative L2 theta 2 dot plus theta 3 dot. And we can see that what we just computed here is equivalent to M. And so we've just confirmed that M indeed relates these two vectors to each other. Okay, so now that we've done that, we can look at part D. And part D asks us what the instantaneous body velocity of the origin of the tool frame is. And so we just found this matrix that relates coordinates with velocities, so we can use that. So we can say that the instantaneous body velocity of the origin of the tool frame, say VBQT, is equal to this matrix M, right? Multiplied by QT. Where QT here is 0, 0, 0, 1, because it's the origin of the frame with respect to, expressed with respect to that same frame, right? So we just get all zeros at the top, and then a 1 to make it homogeneous. And then to make this a little more accurate, I can add a line up here to indicate that it's homogeneous. Okay, and if we do this matrix multiplication here, what we'll end up with is just this last row. So we get that VBQT is equal to negative L1 theta 2 dot, L1 theta 1 dot, negative L2 theta 2 dot plus theta 3 dot, and then 0. Okay, you can kind of see that because this 1 here just pulls out this last column, whereas these 3 zeros zero out anything in front of them. Okay. Sorry, that's a little bit messy, but hopefully that gets the idea across. Next, we have part E, which wants us to sketch the instantaneous body velocities from each joint on the figure below. So for the instantaneous body velocities, that's, I guess, just saying the linear velocities. So you can do this with the circle method that we saw earlier. So using the side view, we can do these two joints. So I believe this is joints 2 and 3, right? So we'll just draw a circle, center at this joint, and then draw a tangential vector. Okay, so this corresponds to twist 3 right here. That's the tangential velocity. And then for twist 2, we again draw a circle. This time it's like this, right? And that gives us a vector like this. Okay? For the top view, pretty much the same thing. We'll center a circle at the joint, pass it through the body, use the right-hand rule to figure out the direction it's going, and then draw a tangential vector. And then we'll label these just to be clearer. And then maybe specify the lengths, I guess. So this guy right here should be L1. This guy should be L2. And then this guy should be square root of L1 squared plus L2 squared. And for each of these lengths, all I did was take the radius of the circle. So the radius of this circle right here is L1. The radius of this circle right here, oops. The radius of this circle here, which creates this tangential vector, is L2. So I think that's all there is to it. Question 6 is on wrenches, and it wants us to look at the manipulator in Appendix 1, Figure 5. So let's look at that. So that's just the manipulator in this configuration right here, where the joint angles are 0, -pi/2, and then 0. So one interesting thing to note here is that this frame right here, the tool frame, gets reoriented. So this is now the new z direction, and then the x direction is now upwards. Okay. So let's look at what the questions ask. Part A asks what spatial forces and torques can be applied by the manipulator in this configuration. And the problem also gives us these associated Jacobians, so that might make this a little bit easier than just by visual inspection. So one way I like to think about questions like this is that if you can induce a velocity in a certain direction, you can also induce a force or torque in that direction. So this one right here tells us that you can induce a velocity about the z-axis. Because of that, you can also induce a torque about the z-axis. So you can write tau z. Same goes for the y-axis right here, tau y, and then the x-axis right here, which is fx. Okay. We also see that these three are linearly independent, so each of these terms can be controlled independently. And so when it asks how many of these forces and torques can be controlled independently, we can just write 3. Cool. Part C says that there's a mass m held by the manipulator at the point with tool frame coordinate 0, 0, 0. So that's just the origin of the tool frame. And it wants us to find the body wrench that's associated with this mass. So let's just go back to this diagram here. All we're doing here is adding a mass m here, right? And it's creating a downwards force. This downwards force has a magnitude of mg, so the force is negative mg in the x direction. You can see kind of visually that it's pretty clear there's no torque applied, just because there's no lever arm. So then the body wrench here is just negative mg, 0, 0, 0, 0, 0. The reason why this negative mg is in the x position and not the z position is again because this axis, or this coordinate frame, has been reoriented. So now the x is this vertical. And we're expressing this as a body wrench, so we should be writing all of our forces and torques with respect to the body frame. This negative mg is in the negative x direction. Cool. Part D wants us to use the Jacobians provided to figure out what joint torques are associated with this body wrench. Okay. So we have a standard form for this. We derived this in discussion that the joint torques is equal to the Jacobian transpose multiplied by the wrench, right? So for this wrench is just negative mg and then all zeros. So if we scroll up and we look at this body Jacobian, we see that none of these bottom terms matter because this is all zeros. And this top row is all zeros, and that gets multiplied with our negative mg. So everything just gets zeroed out. The joint torques is equal to 0. And visually, that kind of makes sense, just because if you look at this diagram, right? If I erase all this, if we have a force here going downwards, it's not really acting on any of the joints, right? What that means is that it doesn't require any energy to maintain this position. We can put any mass up here, it doesn't require more torque on the motor's part to hold it up. Okay. And then, oh yeah, okay. I guess I basically just answered part E. We can say that the mass is supported by the structure of the manipulator. It's almost as if we had this sort of rigid body that was just standing there with no joints, and we put a mass on top of it. It's like the same idea. It doesn't require any torque or force to hold this mass up. Okay, so part F, without performing any computation, what is the spatial wrench associated with this body wrench? Explain your reasoning. So for that, we can just do this by inspection. Again, there's clearly no torque. And we do have this vertical downwards force caused by gravity. But now, since it's a spatial wrench, we want to express that with respect to the world frame. So that gets us S is equal to 0, 0, negative mg. And here it's in the z direction because that's the way the world frame is oriented. And then 0, 0, 0. And then we can just say it's the same as the body wrench, but reorient it. Yeah, and that's it for question 6. Okay, let's look at question 7, which is dynamics, and also the last question. So the first part asks for the kinetic energy of the system, which has 2 masses and 3 springs. So the kinetic energy is pretty much solely determined by the masses, so we can just use half mv squared for each of the masses and sum up their respective kinetic energies. So in this case, that'd be half m1 x1 dot squared plus 1/2 m2 x2 dot squared. And then that's the kinetic energy T. Potential energy is V, that is all stored in the springs. So we know that the equilibrium of these springs is that x1 equals x2 is equal to 0 right here. And we also know that the energy stored in the spring is determined by half kx squared. So for the total potential energy in the system, we'll just sum up potential energy in each spring. So for the first spring, we have k1 x1 squared. That's pretty simple. So we're seeing how much the spring is stretched. That's determined by x1. Second one is a little bit weirder, not too bad though. For this one, seeing how much it's stretched, we can look at the distance, or the difference between x2 and x1. So that's x1 minus x2 squared, sure. Then finally, for the third spring, we can do 1/2 k3 x2 squared. Right. So again, we know the equilibriums are when everything is 0, which is why just increasing x2 will directly increase the amount of the spring is stretched. Okay, I think that's it for part A and B. We have the kinetic energy of the system and potential energy of the system now. And we can use these to write the dynamics for the system, specifically using the Lagrange method. To start, we'll write the Lagrangian, which is T minus V. Okay, and then to compute T minus V, we can just take these two things that we already know and squash them together. So this is T right here. And I'll also grab V. Okay, and then just modify it so it's T minus V. So T minus V is equal to, this is T minus V, right? That's all there is to it. Now we need 2 equations of motion, one for each of the state variables, so one for x1 and one for x2, and this will describe the dynamics of the system. Yeah, so since there's no external forces, we can just write that d over dt, partial derivative of L over, or with respect to one of the state variables, dotted, minus partial derivative of L with respect to that state variable is equal to 0. So this is just the standard equation, it's on your cheat sheet. Okay, so we'll just compute each of these terms for both x1 and x2. Start with dl over dx1. And then we can look at, just do this by inspection. It's just a pretty simple derivative. And so none of these terms in t matter, just this guy and this guy. So that's the only thing that contains x1 and x2. Okay, so just take the derivative and we should get negative k1 x1 minus k2 times x1 minus x2. Yeah. We'll do the same thing for x2, so dl over dx2. Take the derivative. So the only terms that matter here are this guy and this guy. And that should get us negative k3 x2 plus k2 x1 minus x2. So again, notice that this negative sign is here, and that's being distributed throughout this v term. Cool. So now we've computed all the partial derivatives L with respect to x. Now let's do this d over dt, dl, dx dot. So dl over dx dot, d over dt. We'll start with x1 dot. And so the only thing that has x1 dot in it is this first expression. And then if we just differentiate it with respect to x1 dot, we get d over dt m1 x1 dot, right? And that's equal to m1 x1 double dot. Same thing for dx for x2 dot, which is equal to d over dt m2 x2 dot. That's equal to m2 x2 double dot. Okay. So now that we know these four things, we can plug them into this form, and that'll give us our equations of motion. So the first one will be m1 x1 double dot minus, I'll just simplify here, plus k1 x1 plus k2 x1 minus x2 is equal to 0. The second will be m2 x2 dot double dot plus k3 x2 minus k2 x1 minus x2 is equal to 0. And that should be it. If you want, you can optionally try to isolate the x double dots. But if you don't, that's all we have for this 2016 midterm.